In this video, I'm going to demonstrate how to perform a multiple linear regression. In this situation, we have a data set that's some survey data, and we've collected various constructs from this survey. And what we're interested in trying to predict is a stress level, the stress level of a group of employees measured using a standardized stress tool. And we want to see if two measures of control, one of them being mastery, another being a measure of control of your own life. These two measures, we're going to see if those can predict someone's level of stress. And so we have two independent variables, a measure of mastery and a measure of control, and we're going to see if that can predict our numeric outcome, which is stress. So all three of these are numeric outcomes, and we're going to go ahead and assume that we've already screened all three of these variables for normality, so that we know that they're normally distributed, which is one of the assumptions that we have in multiple linear regression. And we're going to use these variables to try and predict this outcome. So now that we've met the assumption of normality for our variables, the next thing we want to try and determine is if these two independent variables or predictor variables are related to the outcome, because we know that regression has to be predicated by a correlation between our independent and our dependent variables. And we also want to look to see if our two independent variables might have multicollinearity. So we want our two independent variables to be somewhat related to one another, but not overly related to one another. So if there's a very strong correlation between our two independent variables, usually 0.7 or 0.8 and above, that would be multicollinearity, which means these two predictor variables are essentially measuring the same thing or predicting the same thing. And so there's redundancy there. So we want to have variables that are related but are not redundant. So in order to determine these two assumptions, we're going to go ahead and do a Pearson correlation among our three variables. So we're going to do a Pearson correlation, and we're going to add our three variables. So we've got our two predictor variables, which are total mastery and total control, and we're going to use that to predict this measure of total stress. And so we want to see the relationships of those variables. We're going to go ahead and calculate that. And we're going to look at the raw output here. And so what we can see here, first of all, is our two predictor variables, total mastery and total control, have a moderate correlation with one another, 0.527, which is kind of right in the middle. So they are correlated to one another, but not highly so. So they measure similar constructs. In other words, they're related to one another, but they don't measure the same construct. And then the next thing we want to look at is the relationship between our two predictor variables and our outcome variable, which is stress. And we can see that they are related to one another at a statistically significant level. So we know that there is a good correlation between our predictors and our outcome, so we should be able to develop a fairly accurate regression model. And so we're going to go ahead and move forward using these two particular variables. Now, if we had multiple variables we wanted to look at beyond two to include in our model, we would look at this relationship. So if we had one of these variables maybe had a very low correlation that was non-significant, then we wouldn't include it in the model. And if we have multiple of these variables, we want to include the ones that have the strongest correlation with the outcome. In this case, both of these are moderately correlated, but they're statistically significant in their correlation. And so we'd be able to add these two without any problem. And so if we had multiple independent variables, we'd again look at that multicollinearity potentially between those multiple independent variables. And if we had a pair of variables that had a correlation, let's say of 0.9, then we're going to want to eliminate one of those variables because we know we've got multicollinearity. So we've got some redundancy there. So we want to look at how these variables are related to one another and look for the variable that seems to be highly related to the others, and that's the one we'd likely eliminate. Another technique we can utilize is we can include all the variables we have and selectively remove one, rerun the analysis, and see how that changes the R-squared value. The R-squared value is the primary determinant we have of making a decision that this is a good model. And so we want to maximize the R-squared value while minimizing the number of variables we have. So we want to get the strongest possible R-squared with the fewest number of variables. So we can do what's called a stepwise regression. We can enter all the variables in and remove the weaker ones one at a time and see how that changes the R-squared value. So that's another type of technique we can use to kind of decide which variables to include in the final model. But in this case, we've only got the two, and we're going to include both of them in the model because they are not highly correlated with one another, but they are correlated well with the outcome. So now we're ready to go ahead and run our linear regression. So we're going to go to the regression analysis model or option. And so our dependent variable, as we mentioned, is the total stress. So we're going to find that in our menu here. Click confirm, and now we're going to find our two independent variables that we're going to include as our predictors. And so that's our total control and total mastery, which is over here. Okay, and we're going to go ahead and click confirm, and then click calculate. And so what we want to do here, here we're in our raw data. We've got several tables. One of the things we can do to determine if we might have multicollinearity, in other words, if we've got a situation in which we've got independent variables that are highly correlated with one another, another thing we can use to determine that is something called the variance inflation factor. And what we look for is the variance inflation factor for each of our independent variables. And typically, if this value is higher than 10, then we have multicollinearity present. As you can see here, this value is 1.38, so that's much less than 10. So along with the correlation that we did earlier in this value, we can make the determination that we do not have multicollinearity, so we have met that assumption of doing multiple linear regression. Okay, the next thing we can look at is the model fit statistics. And this will give us an idea of how accurate the model will be in predicting the outcome. And so we've got our two predictors, and how accurate will these two predictors be in predicting our outcome. And so it's basically an ANOVA. So we've got an F score here and a p-value. And we can see this p-value is much smaller than 0.05. So we can make the conclusion that our model is a statistically significant predictor of our outcome, which essentially means it's better than predicting by chance. And so that's a good sign. So we have a significant model, and we'd like to see that. If it's non-significant, then that would indicate that our predictors aren't doing a very good job of predicting the outcome. But as we can see here, we have a significant model. The next thing we can look at is the R-squared value. And we can see here we've got an R-squared value of 0.466. So that's essentially saying that our two predictors explain 46% of the variance in our outcome. So our measures of control and mastery appear to predict about 46% of the variance in total stress. So that's pretty close to what we would call clinically significant. We like to see a 0.5 or greater in these situations, but that's pretty close to being clinically significant. Now the next thing we can look at are the coefficients. So as this table is arranged, the very first row is the intercept. So that's the y-intercept value in our linear regression equation. And then we have the slope value for our first x variable, which is total control. And we can see what that slope value is. And then here's total mastery, and we can see what the slope value is for that x variable. So when we can create our regression equation, it would be y equals negative 0.175 times a total control score plus negative 0.621 times a total mastery score plus 50. And so that would be our actual regression equation that we could then plug known control values and known mastery values and then predict total stress. Now another thing we can look at is the relative contribution of each of our independent variables to predicting our outcome. So we're going to use this column labeled beta. And so what we look for is the value that has the highest value, and we ignore the negative sign. And so we're looking for the variable that has the highest value. And in this case, total mastery has a 0.422, and our total control has 0.358. So we can see that total mastery explains the majority or a larger proportion of the variance of stress. And we can see over here in the p-value column, it does so at a statistically significant level. And then we can see that total control has a very similar proportion of explaining variance, and it is also statistically significant. Sometimes we can see situations in which we might have one predictor variable explaining more of the variance than another, and maybe one is not statistically significant and the other is. And so that's something we can look for. But we could say with pretty good confidence that total mastery explains more of the variance in stress than total control does. But they explain a very similar amount of variance, and that amount of variance in total is 46%. And so what we can say here, we conclude here, is that total control and total mastery can statistically have their model, and their ability to predict total stress is statistically significant, and the R value is R squared value is 0.46, so about 46% of stress can be explained by the combination of total control and total mastery. Total mastery seems to explain a little bit more of that variance than total control, but it's a very similar amount, and both of those predictors explain variance at a statistically significant level. So that's how we go about running a basic multiple linear regression and interpreting it. As I mentioned before, if we have more than just a couple variables, we have a couple different strategies of how we can determine which variables to include. So if I had a third variable, I could now add that in, rerun the regression, and see how that changes our R squared value, and see how that affects the beta values. Maybe it will increase the R squared value. If that's the case, if it increases the R squared value by, let's say, 5% or more, then I want to include that in my model. If it doesn't have an effect to that degree, maybe it only increases the R squared value by 1%, or actually makes it worse, then I don't want to include that new variable. And so that's a way we have of kind of adding and subtracting variables, kind of do trial and error to try and find the best combination of independent variables so we can get the best model in predicting our stress, knowing what our independent variable values might be. So hopefully you found this useful, and good luck using this in your own research.